Now, let's consider the electronic structures of solids. The electrons of a single, isolated atom occupy atomic orbitals with discrete energy levels. If two atoms come close enough, their atomic orbitals overlap. The overlap of two atomic orbitals produces two molecular orbitals with different energies. Similarly, if a large number, n, of atoms in a macroscopic piece of solid come together to form a solid, the atomic orbitals overlap each other. The overlap of n atomic orbitals produces n levels. Since n is a very large number, the number of orbitals that overlap with each other is very large. For this reason, the adjacent energy levels are very closely spaced in energy and can be considered to form a continuum, an energy band. Two adjacent bands may simply not be wide enough to fully cover the range of energy. Band gaps are essentially leftover ranges of energy not covered by any band, a result of the finite widths of the energy bands. Like in atoms and molecules, in a band structure, the electrons fill up the bands starting from the lowest state until all the electrons are allocated to a state. As a result, the low-energy bands are filled while the high-energy bands are empty. The Fermi level of a solid is the average energy of a newly added electron to the solid. If the Fermi level lies in at least one band, this band is partially filled and the solid is a metal. In an insulator or semiconductor, the Fermi level is inside a band gap, referred to as the band gap, to distinguish it from the other band gaps in the band structure. The closest band above the band gap is called the conduction band, and the closest band beneath the band gap is called the valence band. The name valence band was coined by analogy to chemistry, since in semiconductors and insulators, the valence band is built out of the valence orbitals. The electron conductivity of solid is caused by the drift of electrons in external electric field. The position of the Fermi level with respect to the band structure is very important for electrical conduction. In an empty band, there are no electrons to conduct electricity. In a filled band, all the states are occupied by electrons so that they cannot increase their energy, i.e. accelerate, when an electric field is applied. So, only partially filled bands can conduct electricity. It explains why metals are good electron conductors. In a semiconductor, the band gap is small enough so that the electrons in the valence band are thermally excited to the conduction band. The electrons in the conduction band are referred to as the electrons, to distinguish them from the other electrons in the semiconductor. The unoccupied states in the valence band are referred to as the holes. In external electric field, the electrons drift like free electrons. Meanwhile, the holes are occupied by other electrons, leaving new holes behind. Therefore, a hole can be viewed as a positively charged particle. Both the electrons and holes are referred to as charge carriers. There is no clear boundary between semiconductors and insulators. Typically, semiconductors have band gaps lower than 4 eV. For example, diamond and silicon have the same crystal structure. Diamond is a typical insulator for its 5.5 eV band gap, while silicon is a typical semiconductor for its 1.14 eV band gap. Due to the differences in the concentrations of charge carriers, solids have diverse resistivities. Metals have very low resistivities due to their rich free electrons. In contrast, insulators have extremely high resistivities due to the lack of charge carriers. Since the density of charge carriers decrease with band gap at a certain temperature, the resistivities of semiconductors increase with the band gaps. A semiconductor cannot absorb photon, which has lower energy than its band gap. It can absorb a photon which has higher energies than its band gap, during which a pair of electron and hole is generated. Then, the electron relaxes to the bottom of the conduction band, and the hole relaxes to the top of the valence band. Finally, the electron and hole can recombine to emit a photon of the energy of band gap. This phenomenon is called fluorescence. For example, cadmium selenide's band gap decreases with the particle size. So, under the same ultraviolet illumination, smaller particles fluoresce light with shorter wavelengths. A dopant is a foreign element intentionally added to a semiconductor crystal in a process known as doping for the purpose of giving it different electrical properties. An intrinsic semiconductor is a semiconductor without any significant dopant species present. In an intrinsic semiconductor, the Fermi level lies at the middle of the band gap. The numbers of electrons and holes are equal. The current which will flow in an intrinsic semiconductor consists of both electron and hole currents. The electrons which have been freed from their lattice positions can move through the material. Meanwhile, other electrons can hop to fill the holes left by the freed electrons. An extrinsic semiconductor is one that has been doped. In an extrinsic semiconductor, it is the dopant that mainly provide the charge carrier. The more abundant charge carrier is called majority carrier, which is primarily responsible for current transport. The less abundant charge carrier is called minority carrier. An electron donor is a dopant which releases conduction electrons when incorporated in the crystal. An extrinsic semiconductor that has been doped with electron donor is called an N-type semiconductor because the majority carrier is negatively charged. In an N-type semiconductor, the Fermi level is greater than that of the intrinsic semiconductor and lies closer to the conduction band than the valence band. For example, a common dopant for silicon is phosphorus, which has one more valence electron than silicon. An electron acceptor is a dopant which accepts electrons from the crystal, creating holes. An extrinsic semiconductor, which has been doped with electron acceptor, is called a p-type semiconductor, because the majority carrier is positively charged. In a p-type semiconductor, the Fermi level is below the intrinsic semiconductor and lies closer to the valence band than the conduction band. For example, a common p-type dopant for silicon is boron, which has one less valence electron than silicon. A p-n junction is a combination of p-type and n-type semiconductor materials in a single crystal. At the junction, some of the electrons in the n-type diffuse into the p-type due to higher electron density in n-type. In a similar way, some of the holes in the p-type diffuse into the n-type. As the electrons and holes diffuse, they combine and cancel each other out at the junction. Therefore, the region near the p-n interface loses most of its charge carriers, forming the depletion region. Due to the diffusion of charge carriers, the n side is positively charged and the p side is negatively charged. This creates a built-in electric field, which causes the drifts of charge carries in the opposite directions of their diffusions. Finally, the diffusion current and drift current cancel out each other, so that the net charge carrier flow and current are zero. The built-in voltage is the electric voltage difference between the p-type and n-type at equilibrium. It is the integral of the built-in field across the depletion region. The built-in voltage raises the band energies of p-type, lowers the band energies of n-type, and levels the Fermi level of the whole material. Therefore, at equilibrium, the band structure in the depletion region is bent. In forward bias, the p-type is connected to a high potential and the n-type to a low potential, so that holes are injected into the p-type and electrons into the n-type from the leads. A forward bias lowers the p-type band edges to be closer to the n-type by the amount of the applied voltage. The depletion region narrows as electrons from the n side and holes from the p side diffuse into it. The electrons diffusing into p-type recombine with holes. In a similar way, the holes diffusing into n-type recombine with electrons. With reverse bias, the p-type is connected to a low potential and the n-type to a high potential, so that holes are extracted from the p-type and electrons from the n-type. The p-type band edges are raised relative to the n-type by the reverse bias. The depletion region widens as holes are pulled away from it to the p side and electrons to the n side. Thus, any current is due to the very weak process of carrier generation inside the depletion region. The p-n diode is a type of semiconductor diode based upon the p-n junction. In a p-n diode, the p side is called the anode, the n side is the cathode. The p-n diode conducts current in only one direction. Among many uses, diodes are found in rectifiers to convert alternating current to direct current. In the light-emitting diode, the recombination of electrons and holes is accompanied by emission of light of a wavelength related to the energy gap, so the LED converts a portion of the forward current into light. A photodiode is a diode sensitive to light. In the photoconductive mode, a reverse bias is applied to the photodiode. When light is absorbed by the semiconductor, electrons are excited from the valence band to the conduction band, producing electron-hole pairs. If the electron-hole pairs are created in the depletion region, the built-in field sweeps the electrons to the N side and holes to the P side, and current is introduced. This can be used for light detection and measurement applications. A solar cell is an electronic device that converts the energy of light directly into electricity by means of the photovoltaic effect. Like photodiode, when the light is absorbed, electron-hole pair are produced. In the depletion region, the built-in field sweeps the electrons to the N side and holes to the P side, producing an excess of majority charge carriers and an open circuit voltage.